Welcome to the Deep Dive. Today we're diving headfirst into, a pretty weird place. Quantum physics.
It definitely challenges how you think things work.
Yeah, it's like stepping into this unseen realm that messes with your everyday intuition. And the craziest part, it all kind of kicked off because of a light bulb.
That's right. You got to picture Berlin, late 1890s, all these engineering firms. They're racing, for the best light bulb patents, super high-tech stuff for the time.
Right.
But nobody guessed this everyday gadget was about to, crack open this huge scientific mystery about light itself.
It's amazing, isn't it? Something so normal leading to something so out there. Einstein even said, everything we call real is made of things that cannot be regarded as real.
Whoa.
Yeah. Let that sink in, especially now, reality feels complex anyway. This is sort of a perfect way to see just how weird the universe actually is underneath.
Totally. So today we're going to break down some of those core ideas that popped up. We'll hit the ultraviolet catastrophe, the photoelectric effect, wave-particle duality.
Which is super strange.
Oh yeah, and how we figured out atoms. And even what quantum reality means. It's basically the instruction manual for, everything.
Okay, let's start there. The light bulb. How does a hot wire glowing launch a revolution?
Well, it boils down to something called black body radiation. Basically, how stuff glows when it heats up. Think about a stovetop burner, that filament.
Okay.
Scientists like Max Planck, they hit a wall. They couldn't figure out why hot things don't just keep spewing out higher and higher energy light, into the ultraviolet range and beyond.
Right. You heat metal, it goes red, then orange, maybe yellow.
Exactly. But it never really gets intensely blue or violet, does it? Classical physics, though, predicted it should.
It should just keep getting bluer and bluer, essentially.
Infinitely so, according to the math back then. They called it the ultraviolet catastrophe because the prediction was just disastrously wrong compared to reality.
The catastrophe sounds about right. So, huge problem. How did Planck fix it?
Planck did something really, really radical for the time. He basically said, okay, what if energy isn't smooth? What if it comes in little packets, discrete chunks? He called them quanta.
Quanta. So not like a continuous flow of water, but more like getting water in specific sized bottles.
That's a great way to put it. Yeah, you can only have these amounts of energy, not anything in between. It totally broke from classical thinking. And that idea, that's ground zero for quantum mechanics.
Okay, so energy comes in packets. How does that link back to the light we see?
Planck found this direct link. The higher the frequency of the light, think blue or ultraviolet, the more energy each of its quanta carried.
So blue light packets have more punch than red light packets.
Exactly. Red light quanta have less energy. It was sort of a mathematical trick at first, but it perfectly explained why you don't get that infinite ultraviolet light. Those high energy quanta are just, harder to make at normal hot temperatures.
Okay, that makes sense. Planck solves the light bulb thing with quanta. But then there was another weird light thing, right? The photoelectric effect.
Yeah, another puzzle. Scientists noticed shining intense light, like from arc lamps they used in spark gap experiments for radio waves, onto metal seemed to help sparks jump.
Okay.
So they got more precise, used things like a gold leaf electroscope, and the results were baffling. You could blast red light, really bright red light, at a metal plate, nothing, no electrons knocked off. But then even a faint blue or ultraviolet light, zap, electrons came flying off.
So that's completely backward from what you'd expect. Brighter light should mean more energy, shouldn't it?
That's what classical wave theory predicted. More intensity, more energy should knock electrons harder, but nope. It was the color, the frequency that mattered. Blue light just had what it took, red light didn't, no matter how much red light you used.
Okay, mind officially starting to bend. And Einstein jumps back in here, taking Planck's quanta idea further.
He did. In 1905, same year as special relativity, believe it or not, Einstein proposed that light itself is made of these particles, these quanta, what we now call photons.
So light isn't just a wave, it's also like a stream of tiny particles.
Exactly. And each photon particle carries an energy determined only by its frequency, its color, like Planck suggested.
Okay, let's try an analogy, like throwing marbles at something.
Perfect. Think of electrons in the metal as targets. Red light photons are like lightweight marbles. You can throw billions of them, but they just don't have enough oomph to knock an electron out.
Right.
But a blue or UV photon, that's like a heavy, fast marble. Even just one hitting an electron can knock it clean out of the metal.
Got it. So that explains why dim blue light works, but bright red doesn't. And it ties back to Planck's quanta. Those high-energy UV photons are just rarer.
Precisely. It nailed both problems. But it meant physics had to accept this totally weird idea. Light is both a wave and a particle. Wave-particle duality, that was revolutionary. Physics needed a whole new approach.
Okay, light is weird, wave and particle. What about matter? Like the atoms, everything's made of. How did quantum ideas change our picture of the atom?
Well, around 1911, Ernest Rutherford did his gold foil experiment. Back then, the model was kind of a plum pudding positive goo with electrons stuck in it.
Sounds delicious.
Aha, yeah. But Rutherford shot these tiny alpha particles, which are positive, at super thin gold foil. Most went straight through, as expected.
But not all.
But some bounced back, like really sharply. Rutherford was stunned. He said it was like firing a cannonball at tissue paper and having it bounce back at you.
Whoa. Okay, so what did that mean?
He figured the atom must be mostly empty space, but with a tiny, super dense, positively charged center of the nucleus. And the electrons must be orbiting it, kind of like planets around a sun.
Okay, a mini solar system, but wait. Classical physics has a problem with that too, doesn't it?
Yeah.
Electrons orbiting are accelerating, right? They should radiate energy away.
Exactly. They should lose energy constantly, spiral inwards, and crash into the nucleus in like a fraction of a second. Atoms shouldn't be stable. Another catastrophe.
So Rutherford's model fixed one problem but created a huge new one.
Yep. Until Niels Bohr came along in 1913. He basically said, okay, let's apply Planck's quantum idea to the atom. He proposed electrons can only exist in specific orbits, like designated tracks.
Not just anywhere.
Nope. Only certain orbits with specific fixed energy levels are allowed. And while they're in one of these special orbits, they just don't radiate energy, they're stable.
Okay, so they have these safe zones, like specific lanes on a highway.
Kind of, yeah. And they can only jump between these lanes, these energy levels. If an electron jumps down to a lower energy orbit, it has to spit out the energy difference as a photon of light.
And the energy of that photon corresponds to a specific color.
Exactly. That explained those weird, specific lines of color scientists saw when they looked at light emitted by atoms, the atomic spectra. Bohr basically quantized the atom itself.
Wow. Okay, so energy is quantized, light is quantized, electron orbits are quantized. This quantum stuff is everywhere. But then it gets weirder again with matter, right? De Broglie.
Louis de Broglie,
Yeah.
In 1924, he asked this amazing question. If waves, like light, can act like particles.
Could particles like electrons act like waves?
Exactly. He flipped the script. Seemed totally nuts at the time. We think of electrons as tiny little balls, right? Not spread out waves.
So he suggested maybe everything has this dual wave particle nature.
He proposed just that. He even came up with an equation for the wavelength of a particle, the de Broglie wavelength linked to its momentum and Planck's constant. Pure theory at first, but incredibly bold.
And someone actually proved this, that electrons can act like waves.
They did. The Davison-Germer experiment. Mid-1920s, they were shooting electrons at a nickel crystal, just studying how they scattered.
Okay.
Then, sort of by accident, they heated the nickel crystal, which changed its structure into nice regular layers, and suddenly the scattered electrons weren't just bouncing off randomly.
What are they doing?
They were creating interference patterns, just like light waves do when they pass through two slits or a diffraction grating. The electrons were diffracting, bending around the crystal atoms and interfering with each other.
Electrons interfering with each other like waves. That's hard to picture.
It really is. But it was undeniable proof. Electrons have wave properties. It supported de Broglie and this idea of superposition too, that an electron can, in a way, explore multiple paths at once, like a wave spreading out, until you measure it.
Okay, so wave-particle duality is real for matter too. This quantum world is just bizarre. How did physicists even start to write down the rules for this? The math must be intense.
It got pretty abstract.
Yeah.
Werner Heisenberg, 1925, took a radical approach. He said, forget trying to picture orbits you can't see. Let's just focus on what we can measure.
Like the energy jumps, the light emitted.
Exactly, observable quantities. He developed something called matrix mechanics. It used, matrices, arrays of numbers to represent things like energy and momentum and calculate the probabilities of transitions between states.
Matrix mechanics.
Yeah.
Sounds intimidating.
It was, and fundamentally probabilistic.
Right.
No nice smooth orbits, just probabilities. And one really weird thing came out of it. Non-commutativity.
Non what?
Commutativity. Usually in math, A times B equals B times A, right? Order doesn't matter.
Yeah.
But in Heisenberg's matrices for quantum properties like position and momentum, AB did not equal BA. The order you did the operations, or conceptually, the order you measured things mattered. It changed the result.
Wait, Measuring position, then momentum gives a different answer than measuring momentum than position? That's nuts.
It's a core feature of quantum mechanics. Around the same time, though, Erwin Schrödinger came up with a different mathematical approach, wave mechanics.
That sounds a bit more visual.
It was, in a way. He used wave functions, mathematical waves, to describe particles. He thought of the electron less as a point, more as a matter wave spread out in space.
Okay, so the wave function describes this electron wave.
Yeah. And Schrödinger actually hoped his theory would be deterministic, like classical physics. He thought the wave function was a real physical wave, evolving smoothly over time, predictably.
But that's not quite how it turned out, is it? I sense a twist.
Well, Max Born proposed a different interpretation. He said the wave function itself isn't the physical wave, but its square tells you the probability of finding the particle at a certain point if you look for it.
Probability again. Back to Heisenberg's idea almost.
Exactly. And this probabilistic view became central to the dominant interpretation, the Copenhagen interpretation. Schrödinger really didn't like this randomness.
Which led to his famous cat paradox.
Precisely. Schrödinger's cat wasn't a real experiment, it was a thought experiment. He wanted to show how absurd it seemed if you applied these quantum probability rules, like a particle being in multiple states at once, to a large object like a cat. A cat being both alive and dead until you open the box. He thought that was ridiculous.
Yeah, it highlights the weirdness when quantum meets everyday scales. So let's talk Copenhagen. Bohr and Heisenberg's view. What's the core idea?
The Copenhagen interpretation basically says quantum systems don't have definite properties like position until you measure them. Before measurement, they exist in a superposition of possibilities described by the wave function.
A superposition. Like being multiple things at once.
In a probabilistic sense, yeah. The wave function tells you the odds for each possibility. Then, the act of measuring forces the system to choose one state. The wave function collapses.
So the observer or the measurement isn't just watching. It's actually creating the reality we see at that moment.
That's the provocative idea. It gives the observer a really crucial role. And tied into this is Heisenberg's uncertainty principle.
Right. Can't know everything perfectly at once.
Exactly. You can't simultaneously know both the exact position and the exact momentum of a particle. The more precisely you know one, the less precisely you know the other. And it's not just about bad instruments, it's a fundamental limit baked into nature.
Wow. And Bohr added complementarity.
Yeah, Bohr's principle of complementarity tried to make sense of wave-particle duality. He said an electron can show wave properties or particle properties depending on how you set up your experiment to measure it.
But not both at the exact same time in the same measurement.
Correct. The wave and particle aspects are complementary. You need both concepts for a full picture, but they're mutually exclusive in any single observation.
Man, my head is spinning. It's like the universe plays by totally different rules down there.
It really does, and it gets even stranger with quantum entanglement. This is the thing that famously freaked out Einstein.
Spooky action at a distance. That's his phrase, right? What is entanglement?
It's this bizarre connection you can create between two or more particles. Say you create two electrons together in a specific way. Their properties, like spin, become linked. Inseparable.
Okay.
Now, separate them. Send one to the moon, keep one here. The instant you measure the spin of the electron here, say you find it spin up, you instantly know the one on the moon must be spin down.
Instantly. Faster than light. That sounds like it breaks relativity.
That's exactly why Einstein hated it. He called it spooky action at a distance. He believed in local realism that distant objects have definite properties independent of measurement, and nothing can travel faster than light. Entanglement seemed to violate both.
So he thought quantum mechanics must be incomplete, missing something.
Yes. He thought there must be some hidden instructions, hidden variables that the particles carried with them from the start, telling them how to behave when measured. Like knowing you have one red glove and one blue glove in two boxes opening one box doesn't change the color of the other glove, it just reveals what was already there.
So he tried to show this with the EPR paradox.
Right. Einstein, Podolsky, and Rosen wrote a famous paper arguing that entanglement meant quantum mechanics couldn't be the whole story. If you could know the state of the distant particle without touching it, it must have had that state all along. Reality should be definite, independent of us looking.
He really pushed back hard against the weirdness.
He did. He just couldn't accept a reality that seemed based on chance and these non-local connections. He wanted a deeper, deterministic explanation.
But the quantum story kept unfolding. Dirac came along and found antimatter out of an equation.
Paul Dirac, yeah, 1928. He was trying to combine quantum mechanics with special relativity to describe electrons properly, especially fast-moving ones. He came up with this beautiful equation.
A Dirac equation.
Right. It worked perfectly for describing electron properties, like their spin, but it had a weird quirk. It predicted particles with negative energy.
Negative energy? What does that even mean?
Nobody really knew. Some thought it was just a mathematical fluke. But Dirac made this incredibly bold leap. He said, maybe these aren't negative energy electrons, maybe they're new particles. Like electrons, but with the opposite charge, antimatter.
He predicted the positron, the anti-electron.
He predicted the positron, yeah. A particle with the electron's mass, but a positive charge. And just a few years later, 1932, Carl Anderson actually found it in cosmic ray experiments.
Wow, that's stunning. An equation predicts a whole new type of matter, and then they find it.
It was a massive triumph for theoretical physics, showed how deep these quantum ideas went.
And speaking of electrons and atoms, there's another crucial rule, Pauli's exclusion principle. Sounds important for chemistry.
Absolutely fundamental. Wolfgang Pauli figured out in 1925 that no two identical fermions, electrons or fermions, can be in the exact same quantum state in the same atom.
Same quantum state, meaning same energy, same orbit shape, same spin, the whole deal.
The whole quantum shebang. Every electron in an atom needs its own unique quantum address. Think of it like seats in a theater, only one person per seat.
Okay. They can't all just pile into the lowest energy level.
Exactly. They have to fill up the energy levels progressively, occupying distinct states. This dictates the whole structure of the electron shells around an atom.
And that determines how atoms bond and react. Chemistry.
That's the basis of the entire periodic table and all of chemistry. Why different elements behave the way they do. Why carbon forms 4 bonds. Why noble gases are inert. It all comes down to how electrons, obeying the Pauli principle and quantum rules, arrange themselves. Especially considering their spin, usually 2 electrons per orbital, spins opposite.
So these quantum rules aren't just abstract, they build the world we see.
They absolutely do, from atoms to molecules to materials.
Okay, we have particles, waves, rules for electrons. What about the forces between them? Like electromagnetism. How does quantum mechanics handle forces?
That led to the development of quantum field theory, or QFT. This was the next big step, really trying to merge quantum mechanics with special relativity properly.
QFT, what's the core idea there?
It shifts the perspective. Instead of particles being the fundamental things, QFT says the fields are fundamental. There's an electron field permeating all space, a photon field, and so on.
And particles are just ripples in these fields.
Exactly. Particles are excitations, like little bundles of energy within their underlying field, and forces. Forces arise from the exchange of particles between fields.
So the electromagnetic force between 2 electrons isn't action at a distance, it's them tossing photons back and forth.
That's the picture. Photons are the force carriers for the electromagnetic field. QFT provided a framework to describe not just electromagnetism, but also the weak and strong nuclear forces, all mediated by exchange particles. It naturally handles particle creation and annihilation, antimatter. It's the foundation for the standard model of particle physics.
The standard model, that's our best current picture of fundamental particles and forces, right?
Pretty much, yeah. And within QFT, the theory describing electromagnetism, the interaction of electrons and light, is called quantum electrodynamics, or QED.
QED. And this one is supposedly super accurate.
Astonishingly accurate. Developed largely by Feynman, Schwinger, and Tamanaga in the 40s. QED describes how electrons, positrons, and photons interact.
And Feynman diagrams help visualize this.
Immensely. Feynman came up with these simple diagrams, lines, and squiggles that represent particles interacting, exchanging photons, being created or destroyed. They make calculating incredibly complex processes much more manageable.
Like a graphical shorthand for the math.
Exactly. And the predictions QED makes, like the precise magnetic properties of the electron, match experiments to an unbelievable number of decimal places. It's probably the most precisely tested theory in all of science.
Okay, wow. But let's loop back to Einstein's ghost. His skepticism about entanglement and hidden variables. Did we ever figure out if he might have been right?
Well, that question lingered for decades. Then, in the 1960s, a physicist named John Bell figured out a way to actually test it.
Test hidden variables. How?
Bell devised a theorem, Bell's theorem. It basically showed that if reality is based on local hidden variables, Einstein's view, then measurements on entangled particles must obey certain statistical correlations described by Bell inequalities.
Okay, so a mathematical limit based on local realism.
Right. But crucially, standard quantum mechanics predicted different correlations, ones that would violate Bell's inequalities. So it set up a direct experimental test.
Oh.
Measure the correlations. Do they obey Bell's rules or quantum mechanics rules?
A showdown between Einstein and Bohr, essentially, decided by experiment.
Pretty much. Starting in the 70s with Clauser and Friedman, then more refined experiments by Elaine Aspect and others, they performed these delicate measurements on entangled photons.
And the results? Drumroll.
The results consistently, unambiguously violated Bell's inequalities. They matched the predictions of quantum mechanics perfectly.
So, spooky action at a distance is real. Einstein was wrong on this.
It seems so. The experiments strongly suggest that local hidden variables can't explain quantum entanglement. Reality, at its core, seems to be non-local in this strange quantum way. The universe is weirder than even Einstein thought.
That's incredible. So where does that leave us now? Is quantum mechanics the final story, the ultimate theory? Or is it just a really, really good approximation of something deeper?
That is the big question. Quantum mechanics is incredibly successful. It describes so much. But is it complete? Some brilliant people like Roger Penrose argue maybe not.
Why? What might be missing?
Penrose, for instance, thinks we won't have a truly complete picture until we can unite quantum mechanics with general relativity, Einstein's theory of gravity. We need a theory of quantum gravity.
The holy grail of physics.
Exactly. Maybe that deeper theory will explain some remaining mysteries, like why measurement causes the wave function to collapse, or maybe even shed light on consciousness, as Penrose speculates. He thinks there might be something deeper, perhaps still deterministic, hiding beneath the probabilities.
So maybe quantum mechanics isn't the basement level of reality, just a very important floor.
That's one way to think about it. And while quantum computing is super exciting and uses quantum principles, Penrose and others might say it doesn't necessarily get us closer to understanding that fundamental nature of reality or resolving these deep interpretational questions. The debate about what quantum mechanics means is still very much alive.
What a journey. From a light bulb puzzle to questioning the very fabric of reality. It's mind-blowing that these bizarre ideas are now behind so much technology, semiconductors, lasers, medical scans, potentially quantum computers.
Absolutely. It's gone from weird theory to engineering reality. But yeah, it really makes you wonder, doesn't it? Does all this strangeness, this non-locality, this observer effect, does it point to even deeper layers we haven't uncovered?
Maybe something linking quantum physics and gravity, or even consciousness.
Who knows? It could require a whole new revolution in thinking. But it definitely tells us there's still so much we don't understand. The quest is far from over.
A fantastic place to leave it for today. Definitely gives us all something to chew on. Thanks for joining us on this quantum deep dive. Until next time, keep questioning.